Gas chromatographs require strict temperature control. As a result, the sample injection valve, column, and detector are housed in a thermal enclosure called the oven. Oven operations can take place at a wide range of temperatures, since consistency is the purpose of temperature control. Operating temperature can be as low as 10 and as high as 225 degrees Celsius, but it should remain constant. Safety is a major consideration during oven maintenance. When maintaining a gas chromatograph, turn off power unless it's necessary for testing procedures. The process sample may be flammable or toxic, and the oven extremely hot. Before you begin, determine sample composition and any special safety requirements for hazardous locations. Also, notify control personnel of where and how long you'll be working, and obtain any required safety permits. In the air bath oven, heated air circulates inside a thermally insulated enclosure. An electrical heater and thermostats monitor and control the oven temperature for safe operation. To expose oven components for maintenance, loosen any latches or bolts that are securing the cover. Examine the inside of the oven for cleanliness. Debris may indicate that the air being circulated through the oven is dirty. There should be no traces of water, oil, or dirt in the oven. If there is an indication of contamination, check the oven air supply system. Check any knockout pots for water or debris, and check the filters. If they're clogged, replace them. In this example, the oven is not heating, so check the heater element. First, turn off power to the oven. Use a multimeter to check the heater element for continuity. To do this, locate the element terminals. On this model, it's not necessary to disconnect the heater leads because the circuit contains a solid-state relay which opens when the power is off. Connect one lead to each terminal and check the resistance reading. A reading of infinity indicates an open element, and a reading of 0 indicates that the element has shorted. Since the heater element is open, we'll replace the heater assembly. Loosen the fasteners that secure the heater and remove it from the oven. Before installing a replacement heater assembly, make sure that the new element meets the requirements of the analyzer and the process. The gas chromatograph column is where separation of the sample components takes place. Most gas chromatographs use columns filled or packed with either liquid on solid support or an active solid. On this gas chromatograph, a comparison between the original calibration chromatogram and a current chromatogram shows that components are no longer separating properly. Further investigation shows that the oven temperature, carrier gas pressure, and all other variables are correct for this application. From this, we can assume that the column is contaminated with water or debris and must be replaced. When replacement of the column is required, first shut off the sample stream and then the carrier flow. Loosen the column fittings and remove the column from the oven. Install a new column that is an exact replacement of the damaged column and secure the fittings. Restart the carrier flow and check for leaks. If there are no leaks, restart the sample stream and return the gas chromatograph to service. After column replacement, the gas chromatograph must be calibrated. Calibration is covered in segment 3 of this tape. In the next segment, you'll learn about gas chromatograph detectors. But for now, review this material in your workbook. In a gas chromatograph, sample components pass from the column to the detector. The detector reacts to each of the components as they exit the column. Based on this reaction, the electronics section measures and records the type and quantity of each component in the sample stream. As with other oven components, detectors are designed to operate over a wide range of temperatures and flow rates, but those factors must remain constant. A thermal conductivity detector uses two thermistors as two legs of a Wheatstone bridge. One thermistor is the reference detector. The other is the sense or measurement detector. The column effluent, which consists of the carrier gas and sample from the column, flows over the measuring detector. Pure carrier gas flows over the reference detector. Because of differences in thermal conductivity, the components and the carrier gas conduct heat and cool the thermistors at different rates. This results in changes in resistance, unbalancing the bridge, and generating a signal that represents the concentration of the sample component. This measurement is usually expressed in percent concentration. The thermal conductivity detector can be used with both organic and inorganic samples. Detector malfunctions may be traced to the detector assembly or the electronics section of which the detector is part. Some tools that may be needed for maintenance of the thermal conductivity detector assembly are a multimeter, small needle nose pliers, soldering iron, magnehelic flow meter, scribe tool, screwdriver, high temperature multi-core solder, and small tweezers. With the analyzer in operation, check that carrier flow from the detector reference vent and the column vent meet manufacturer's specifications. To do this, attach a calibrated magnehelic or other flow meter to the reference vent line. In this case, the reading is correct. Repeat this process with the column vent. If there is no flow, or if the flow has changed from one or both vents, a detector tube may be blocked or restricted, and it should be changed. Next, verify thermistor resistance. To do this, turn off the power to the analyzer. Disconnect the wires of each thermistor at the terminal strip. Use a multimeter to measure the resistance of each thermistor and check for shorts to ground. The measurement or sense thermistor resistance and the reference thermistor resistance should be within 10% of each other. The resistance to ground should be greater than 1 megohm. Remove the detector cover and inspect the thermistor wires for damage or stress. The sense and reference thermistors must be replaced as a set. This is the intercolumn detector, which is discussed in the student workbook. To replace the thermistors, unsolder all leads from their feed-throughs. Remove the two screws and lift the retainer plate away from the detector body. Leave the wires attached. Lift out the thermistors. Install new thermistors in their proper cavities and be certain to align the thermistor leads. With a multimeter, check the thermistor leads to be certain they are not shorted to ground. Reinstall the retainer plate. Position the thermistor leads so that they contact the corresponding feed-throughs. Use high-temperature solder to solder each thermistor lead to its feed-through. In some cases, thermistor block cleaning and repair may be necessary. To do this, remove the thermistors as just described. Remove the Teflon bushings and metal inserts. Run a wire through the detector tubing. Use a syringe to force air through the tube to blow out any loose debris or dirt. Then clean it out with solvent. Verify that the thermistor cavities are clean and dry. Install the metal inserts and position them so that the slots in the bottom are perpendicular to the line of cavities. This allows the sample and carrier gas to flow completely around the thermistor. Install the Teflon bushings on top of the inserts. Install new thermistors in the proper cavities. Replace the cover plate and solder the thermistor leads. Your workbook has additional information on thermal conductivity detectors. In the next segment, we'll review the maintenance for a flame ionization detector. The flame ionization detector works on the principle that, when burned, organic matter will produce a number of ions proportional to its carbon number. In this example, a hydrogen flame, fueled by breathing quality air and hydrogen, burns, creating few ions. When sample component A is introduced into the flame, it burns, producing ions proportional to its carbon number. An electrically charged collector attracts the ions and creates a signal that is amplified and sent to the data collection system. The detector's flame burns continuously and is monitored by a thermocouple inside the housing. If the thermocouple senses that the flame has gone out, an auto-ignite sequence will attempt to reignite it. If the flame still does not ignite, an alarm is triggered. This gas chromatograph contains an intercolumn thermistor detector. Intercolumn detectors and their function are discussed in your workbook. Some tools you'll need to maintain the flame ionization detector are a screwdriver, open-end wrenches, magnehelic flow meter, small tweezers, and 6-inch needle nose pliers. While adjusting the detector flow, the analyzer and the air treater, if used, should be at operational temperature. Turn off the carrier gas, the hydrogen, and the flame air, and wait until they drop to 0. Connect the flow meter to the detector vent. Adjust the hydrogen flow to 28 cc's per minute. You'll skip this step if your system uses hydrogen as a carrier gas. Connect the 800 cc rotometer to the detector vent and adjust the flame air regulator to 500 cc's per minute. Remove the rotometer and adjust the carrier regulator to the proper pressure. When maintaining the detector, the flame must be out and the analyzer power turned off. To turn the flame off, turn the flame fuel regulator, the carrier regulator, and the flame air regulator all the way down. Because hydrogen burns with an invisible flame, it's very important that the pressures are at 0 to ensure the flame is out before you begin your maintenance. One of the most frequently required procedures for the FID is replacement of the burner tip. This can be accomplished while the detector is still in the oven. To replace the burner tip while still installed, remove the sensor and terminal covers from the detector. Loosen the burner clamp. Loosen the screw in the end of the bias ignite electrode. Remove the coax center conductor of the bias ignite cable from the bias ignite electrode. Remove all the nuts and washers from the electrode. Pull out the bias ignite electrode and burner tip far enough to clear the burner tip ferrule and lift the burner tip from the hole in the bias ignite electrode. Don't remove the bias ignite electrode. Insert a new burner tip ferrule in its cavity in the detector body. Install the burner clamp nut over the ferrule and finger tighten it enough to hold the ferrule in place. Insert the long end of the burner tip through the hole in the bias ignite electrode. Align the short end of the burner tip with the hole in the end of its ferrule. Push the burner tip and the bias ignite electrode toward the body until the long end of the burner tip is centered over the collector and the short end is pushed into the ferrule. Tighten the burner clamp nut. Replace the nuts and washers on the collector and replace the bias ignite cable. Be careful not to rotate the electrode. Be certain that all connections are tight. Sometimes it will be necessary to replace the bias ignite and collector insulators. To do this, begin by removing the bias ignite and signal cables from their electrodes. Remove all nuts and washers from the electrodes. Remove the bias ignite and collector ground clamps and lift off the insulator clamp plate. Loosen the burner clamp nut. Loosen the bias ignite electrode and pull out both the burner tip and the bias ignite electrode. Remove the baffle plate from the detector body. Pull out the controller electrode assembly. Push the bias ignite and collector insulators through the detector body and lift them away. Be certain the insulator O-rings come out with the insulators. Place new insulator O-rings in the O-ring cavities in the block. You may need to work the rings into place with a blunt tool. Insert both the bias ignite and collector insulators through the cavities containing the O-rings and press them firmly into place. Place the insulator clamp plate over the two insulators and clamp it in place with the bias ignite and collector ground clamps. Insert the collector electrode into the insulator. Place the baffle plate against the body and slide it over the bottom portion of the collector until the baffle plate holes align with the threaded holes of the body. Insert the bias ignite electrode partway into its insulator. Insert the long end of the burner tip through the hole in the electrode. Align the short end of the burner tip with the hole in the end of the ferrule. Push the burner tip and the bias ignite electrode toward the body until the long end of the burner tip is centered over the collector and the short end is pushed into the ferrule. Slide new electrode O-rings over the bias ignite and collector electrodes. Work the O-rings into the cavities in the insulators. Place a washer and nut on the bias ignite electrode. Tighten the nut. Be careful not to turn the electrode, and be sure the collector ring is centered in the baffle plate. Place a washer and nut on the terminal end of the collector electrode. Tighten the nut. Verify that the burner tip is still centered over the collector and tighten the screw of the bias ignite electrode. Tighten the burner clamp nut. Reinstall both the bias ignite and signal cables on their respective electrodes and ground clamps. Fasten them in place. Detector maintenance should include periodic cleaning according to the manufacturer's specifications. First, turn off the electrical power to the analyzer. Be sure that the carrier, flame fuel, and flame air are shut off. Do not begin cleaning procedures until all gauges indicate 0. Unless you suspect that the block needs replacing, there's no need to remove this detector from the oven when cleaning. Remove the terminal cover and the sensor cover. Remove the bias ignite and signal cables from their electrodes and ground clamps. Remove all nuts and washers. Remove all ground clamps and lift off the insulator plate. Loosen and pull out the burner clamp nut and the bias ignite electrode. Now you can remove the baffle plate. Next, pull out the controller electrode. Push the bias ignite and collector insulators through, making sure that the O-rings come out as well. Remove the burner clamp nut and the thermocouple and its wires. To remove the air filter disc, gently tap it with your fingers. Disconnect and remove the air supply line from the body of the unit. Remove column effluent and hydrogen supply lines. Flush these lines with a solvent by forcing the fluid through them. These are capillary lines and have a low flow rate. Set the lines aside to air dry. Replace any worn or damaged parts. All pieces of the detector, except the air filter disc, should be ultrasonically cleaned to remove any contaminants that could give false indications when the detector is restored to operation. Use a degreaser on each piece to remove the ultrasonic cleaning solvent. Clean all parts with warm soapy water to remove the degreaser, and rinse all parts with distilled water to remove any soap film. Clean all hand tools in the same manner, and be sure to wash your hands. Avoid excessive touching of any of the parts from the sensor side of the detector. Extremely sensitive applications may require the use of protective gloves to handle the detector pieces. Now, use solvent to clean the detector block, then flush it with distilled water and blow dry it with low-pressure air. After all the pieces of the detector have been cleaned, it can be reassembled. Begin by replacing the air filter disc. Insert the thermocouple through its fittings and fasten it in place, and connect the wiring. Install insulator O-rings in the bias ignite and collector cavities. Insert the bias ignite and collector insulators through the cavities containing the O-rings and press them into place. Place the insulator clamp plate over the two insulators and clamp it evenly in place with the bias ignite and collector ground clamps. Insert the collector electrode into its insulator. Place the baffle plate against the body and slide it over the bottom portion of the collector until the baffle plate holes align with the threaded holes of the body. Place the burner tip ferrule in its cavity and loosely fasten it in place. Insert the bias ignite electrode partway into its insulator. Insert the long end of the burner tip through the hole in the electrode. Align the short end of the burner tip with the hole in the end of its ferrule. Push the burner tip and the bias ignite electrode toward the body until the long end of the burner tip is centered over the collector and the short end is pushed into the ferrule. Slide the electrode O-rings over the bias ignite and collector electrodes. Place a washer and nut on the bias ignite electrode. Tighten the nut and be sure the collector ring is centered in the baffle plate. Place a washer and nut on the terminal end of the collector electrode. Tighten the nut without turning the electrode. Measure the insulation resistance of the collector and burner tip. Verify that the burner tip is still centered over the collector and about 1/32 of an inch above it. Tighten the screw in the end of the bias ignite electrode and tighten the burner clamp nut. Be certain that the end of the igniter wire is near the level of the burner tip and about 1/16 of an inch from it. Verify the alignment of the thermocouple, the collector, the burner tip, and the igniter wire. If alignment is incorrect, loosen nuts and screws, realign, and finger tighten the connections. Install the carrier and hydrogen inlets and the air inlet. Install the coax shields of the bias ignite and signal cables. Connect the bias ignite center conductor to the collector electrode. Once all detector components have been properly aligned, tighten any loose nuts or washers. Install the sensor cover O-ring in the sensor cover. Install the terminal cover and the sensor cover. Adjust the carrier, flame air, and flame fuel regulators to their proper settings. Leak check all the connections. Wait for the flows to stabilize and the lines to purge. Turn on the electrical power and restore the system to operation. In the next segment, you'll learn about gas chromatograph controls. But for now, review this material in your workbook. Today's microprocessor-based chromatograph control systems are more flexible and easier to use than earlier models. Based on the requirements of a specific application, a gas chromatograph controller can be configured to automatically control certain functions, such as amplifying and digitizing the detector signal, and integrating the detector signal, identifying the peaks, and calculating component concentrations. It is also capable of automatic calibration, sample injection, activating sample and column valve switching on a cycle clock basis, and activating sample switching valves to switch between multiple sample streams or a calibration stream on a sequential basis. In addition, microprocessors control oven temperature, provide data on measured component concentrations for printed reports, analog outputs, and serial computer links to host computers, and communicate with and control other instruments in the loop over data highways. This analyzer has a keypad interface for operation, maintenance, and programming. Anytime key components, such as the column or detector, are cleaned or replaced, calibration is necessary. To manually calibrate this gas chromatograph, you'll use a standard calibration sample tank. First, be sure that you are familiar with the location of the analyzer's valves and rotometers. Close the Calibrate Standard Flow Control valve. Open the shutoff valve on the Calibrate sample tank and set sample pressure according to specifications. Close the analyzer's sample flow control valve. Adjust the Calibrate Standard Flow Control valve until the analyzer's sample flow rotometer is at the level specified by the manufacturer's guidelines. Now, you're ready to calibrate the chromatograph. Make necessary adjustments to the chart recorder. Select the chromatogram output on the recorder from detector 1. This is normally the main detector. To do this, press detector 1 and chromatogram bar graph on the service panel. Balance the detector by pressing Event 1, 5, and Operate. Set the detector range to 0.2 volts as follows. press 0, Range. The display will prompt you to select Desired Change in Detector Range. Press 2 and enter. The display will show the current range and prompt you to make adjustments by using the up and down arrows. Press the appropriate arrow until the display range equals 0.2 volts. Observe the baseline of the chromatogram for a few minutes. If it's drifting excessively, the detector is probably not quite up to temperature. Wait until the baseline is stable. If some peaks are off scale, adjust the range up. If all of the peaks are too small, adjust the range down. Now, check to see that each component in your calibration standard is correctly entered in the analyzer factor table. To do this, press Factor, 1, 0, 1, and Display. The display will show the current factor, 101. To change the concentration, enter your calibration standard for peak 1 and press Enter. To read and change the next concentration, press Display and enter the calibration standard. Repeat this process for each component in your calibration standard. When you have finished entering the calibration standards, start the calibration by pressing Calibrate. Check and adjust the sample flow rotometer. Allow the calibration to continue until the analyzer is sufficiently stable for at least 3 cycles to repeat within the specified tolerance. While the calibration runs are being made, examine recorded chromatograms to see that all peaks are within the gate and are of expected size. When you're satisfied with the chromatogram, press Hold and wait until the current calibrate cycle is complete. Press Event 10, Operate. This updates the new calibration factors. Turn off the Calibrate flow valve. Now, you can restart the sample stream. ISA's instrument technology training program is general in nature. When performing any instrumentation maintenance in your plant, be sure to follow the specific maintenance and safety procedures provided by your facility and the equipment manufacturer.